Okay, hello everybody. This presentation is going to be about how to find the optimal amount, the optimal bundle to consume using algebra and a little bit of calculus. If you have not already gone through the presentations about the power rule, you definitely need to review that. We're going to be using the power rule here. If you need to look back through and review the PowerPoint about the power rule and also functions of two variables, you need to do that first. Okay, so anyway, this is a similar situation as the last presentation. We've got a budget constraint. We know graphically from the previous presentation that the optimal bundle is going to be at point C that's on this graph, because that's where the indifference curve is just tangent to the budget constraint. So then the question is, how can we find the coordinates of point C, which will tell us the amount of each good that we want to consume using math instead of just looking at a graph? So here's the situation. We have two goods, food and water. Food costs $15 per unit and water costs $10 per unit. So that means that water is on the horizontal axis and food is on the vertical. And from that, we've drawn the graph here, but we're not going to need the graph in order to do the math. So remember what we were talking about in the last presentation is that at this point of tangency, at point C, the optimal bundle, the slope of the budget constraint is equal to the slope of the indifference curve. So we're going to go through three steps. We're going to find the slope of the budget constraint, then we're going to find the rate of change of the indifference curve, and then in step 3, we're going to set those equal to each other and do some solving. So step 1 is to find the slope of the budget constraint. So this is the most familiar thing. I want you to pause it here and figure out what is the slope of the budget constraint in this example. There's a long way and a short way to figure this out. Either way you want to do it, take a second to figure it out. So I'll make a play pause it question about this. Okay, so here I went ahead and figured out the slope using two different methods. First is the way you've been figuring out slope since Algebra 1. I just took the two intercepts and did change in y over change in x. You get the slope is negative 2/3. And then sort of the shortcut way is, as we talked about back when we were looking at budget constraints, the slope of the budget constraint is always just the price of the horizontal good over the price of the vertical good. So I just did negative 10 over 15 because those were the prices that were given in the problem, 10 and 15. And you also get negative 2/3. Either way, you get the same answer. Okay, so that was pretty straightforward. So now we're going to look at how do we find the rate of change of the indifference curve. So finding the rate of change or the slope of a nonlinear function is a new skill for most people. So I'm going to go through this pretty carefully. So here we are given an equation for the utility function. Your utility is a function of food and water. And specifically, utility is given by the amount of water you drink raised to the 3/4 power times the amount of food you eat raised to the 1/4 power. So the way we're going to find the rate of change of the indifference curve is we're going to apply the power rule to this utility function. First, we will apply the power rule as if W is the variable, and then we will apply the power rule as if F is the variable. When we apply the power rule to any function, it gives us a marginal function. So here we're starting off with utility. When we apply the power rule to it, it's going to give us marginal utility. So I'm going to write out the steps of the power function. I want you to go ahead and try to find, go ahead and start by applying the power rule for W, and then we'll check in, and then we'll go from there. Okay, so I'm going to apply the power rule for W and then check back. So go ahead and pause and put in your answer into play pause it. Okay, so here is where I did the power rule. I applied the power rule to the utility function with respect to W, water. So you see this little symbol here is the notation for taking the marginal utility of the function with respect to W. This is a little Greek symbol. It's like a backward 6. It's like a curvy, small, lowercase d. Anyway, I think it's lowercase sigma. Anyway, so remember when we are applying the power rule, we're treating W as if it's the variable. So you bring down the exponent and then reduce the exponent by 1. So I brought the 3/4 down. So that's where the 3/4 in front of W came from. And then I subtracted 1 from W's exponent. That gave me negative 1/4. And then anything else that's not the variable in question, you just leave it alone. So I just left f to the 1/4 alone. So then I did a little bit of simplification. Now W has a negative exponent. It's W to the negative 1/4. So I just brought that down to the denominator. Remember, negative exponents, you can make them positive by moving the base down to the denominator. So that gave me the marginal utility of water is 3f to the 1/4 over 4w to the 1/4. This makes sense. The marginal utility of water is going to depend on how much food and water you've had. So that was applying the power rule to the utility function for water. Now we need to do the same thing, but treat food, f, as if it were the variable. So go ahead. I'm going to pause it again, give you a second to work out your answer to that, and then I'm going to put it up on the screen, and you'll put yours into play pause it. So have fun. Be back in a second. Okay, so here is the marginal utility of food. I applied the power rule, treating f as the variable. Brought down the exponent on f, that gave me the 1/4 here, and then I subtracted 1 from the exponent on f, that gave me negative 3/4. And then since we're treating f as the variable and w is not f, we just left it alone. So that's where this w to 3/4 is. And then again, I simplified the negative exponent, and I got w to the 3/4 over 4f to the 3/4. So this is the marginal utility of food. Okay. Now, to find the rate of change of the indifference curve, we're actually going to take the ratio of the two marginal utilities. And I think we're going to do that on the next slide. But hang on, I want to write down what the marginal utilities were. Okay, so now we're ready to find the marginal rate of substitution. To do that, we're going to put the marginal utility of the good that was on the horizontal axis, which in our case was water, divided by the marginal utility of the good that's on the vertical axis. In our case, that was food. Okay, so I'm going to go ahead and write it out over here. I'm going to pause it while I write, and then I'm going to go through how to simplify it. It looks scary, but it actually simplifies very nicely. All right, so here's a little bit of algebra. So here's what we get when we do marginal utility of water divided by marginal utility of food. 3f to the 1/4 over 4w to the 1/4. That was the marginal utility of water that we got on the previous slide. Down here, we've got the marginal utility of food. Then when you're dividing a fraction by fraction, you take the reciprocal and multiply. So that's what I'm doing here. And then when you simplify, you need to do 3f to the 1/4 times 4f to the 3/4. 3 times 4 is 12. When you're multiplying the same base, you add the exponents. As it turns out, 1/4 plus 3/4 is 1. So we get 12f to the first. And in the denominator, we get 4w to the first. So all those fractional exponents go away. And so then we get that the marginal rate of substitution is just equal to this nice little expression, 3f over w. So now we have figured out the marginal rate of substitution, which was step 2 of the process of finding the optimum bundle. Okay, so let's move on to the next slide. We're going to want to set those equal and set the slope of the budget constraint equal to the marginal rate of substitution. Okay. Oh Lord, I need to pause and go back and remember what the slope of the budget constraint was. Oh, it was negative 2/3, I think. All right, so let's start working on this. So we want to do slope of budget constraint equal to the marginal rate of substitution. Okay, I'm going to pause and write these in and then solve them. So I want you to go ahead and substitute those expressions in and try to solve to get a single expression. You're not going to get the answer from this. We're still going to need to do a little substitution, but go ahead and start writing it out. Okay, I went ahead and set the slope of the budget constraint, which we found in step 1 several slides ago was 2/3, equal to the marginal rate of substitution, which we just found on the previous slide, 3f over w. And then I just solve for one of the variables. It doesn't matter which variable you solve for. I chose to solve for w. You're going to end up getting the same answer no matter which one you do. So what we know at this point is that whatever the bundle we end up consuming, we should consume in a certain ratio. However much food we're consuming, we should consume 4.5 times as much water as that. But that doesn't tell us specifically exactly how much food and water we will optimally end up consuming. It just tells us the ratio. If we know how much food we're having, it tells us how much water we should have. To finish the problem, we're going to have to come back to the budget constraint. So the other piece of information that we haven't used yet is that we need to spend our whole income, which if you go back and look at the original problem, we have $600 for income. And the price of water was $10. And the price of food was $15. So we know that we need to end up on our budget constraint line, which means that we need to spend all of our income. So we know that at the optimal bundle, the amount of money that we spend on water, which is 10 times the amount of water we consume, because the price of water was $10, plus $15 times the number of units of food we consume has to add up to $600. We need to spend all $600. So what I'm going to do is I am going to take this little expression I got for W over here and substitute that into the budget constraint. And then we're going to be able to solve for an exact amount of food and water. So remember, W has to be equal to 4.5 times F. So I'm going to substitute, instead of writing W, I'm going to put 4.5F. Okay, so at this point, I want you to go ahead and finish this and solve for the optimal amount of food and water. I'm going to pause it and finish writing out the solution, but I want you to put your answer into play pause it. I'll be back in a second. Okay, so I just did a little solving here. 10 times 4.5 is 45, so you get 600 equals 45F plus 15F. 45F plus 15F is 60F. Divide both sides by 60, and you get that the optimal amount of food to consume is 10 units. So a lot of times, in notation I use, if I put a star on it, that means the optimal amount. So F star means optimal amount of food is 10. So now that we know that we should consume 10 units of food, there's a couple ways you can go back and solve for how much water you should consume. The first way to do it is to plug back into the budget constraint, which is what I've done here. I just plugged in 10 for F, and then solve for W, and you get that W star is 45. The other thing you can do is you can take 10 and plug it back into the marginal rate of substitution. So now that we know that F is 10, we can plug that in and we'll also get that W star is 45. So, and if you look back on the graph at the beginning of this presentation, the dot that is on the graph does appear to actually be at the point 45 units of food, I think, was on the horizontal axis, and then 10 units, oh no, water was on it. So 45 waters and 10 units of food. And that's the optimal bundle. Oh, we already did that. Okay, so here's some key vocabulary that we went over. You can pause it and review this. And then I think there's optimal rule again, pause. I'm getting to the very end of this time limit. And Okay, here's an example to try. I'm going to pause it and put the answer out here. So, all right, here's a solution.